you have to stay on the topic.
You want to go get me some coffee on your break hour or whatever you call it?
Okay, as you can see, Heather and anyone else who may be absent today, we're good at whining already. Evan wants his coffee.
Yes, I do.
No, I'm not going to go get you your coffee on my planning period.
You just set it in the locker. I wouldn't do that.
Okay. So, we're ready to start what I think of as the algebraic part of trigonometry. The next couple chapters will be a lot of algebra type stuff. Today we are learning what is called the fundamental identities. You did one day of them last spring to have a little bit of an intro to them. Identities get way more exciting than that. Identities are my favorite thing to work. I love these babies. If y'all want to get me a present, go out and buy me a book of trig identities I've never worked before.
Dear God.
It would be hog heaven.
And this will boost our grade, yes?
No, we cannot boost our grade through bribery.
A really good one.
That would be unethical. So my first question to you is, when I say we're going to do identities, what's an identity?
I don't know. We should break down the word, see if we can find something.
Well, what's the identity property that you studied back in Algebra 2? There's the additive identity and the multiplicative identity. And you add what? You get, you add 0, you get the same number back that you started with.
Identity.
Identity means it's got to keep the same value. In our case, identities are true for any value you put in the variable. So it doesn't matter what number you put into the variable, it will be a true statement. Here's an example of a, whoops, we just killed the microphone. An algebraic identity would be something like 2 times x plus the quantity, x plus 5, equals 2x plus 10. If I put 1 in for x, will both sides be equal?
Yep.
Yeah. If I put 30 million in for x, is it going to be equal?
Yep.
Yeah. And that's it's a statement that's true for any value you can put in for x. Okay, we're going to do trig identities. So ours are going to be true for any angle you could put in. So any angle measure in degrees or radians wouldn't matter. These are true for any angle measure you can put in there. Now, I'm hoping perhaps that you will maybe remember some of the trig identities that you learned if I cue you a little bit. Today we're doing what are known as the 8 fundamental identities.
Any valuable what? Proof is valuable what?
Oh. Sorry.
Variable?
That's supposed to be variable. Okay. Okay. That's what I get for talking and writing at the same time. Okay. So they are valuable. So there are 8 what we think of as the fundamental identities because they just come back all the time, over and over and over. These particular 8 are the ones that I will expect you to memorize. The rest of the identities we do in this section you don't have to memorize, but these 8 you have to know because they come back forever, and you have to be able to see them coming at you. You got to know them well enough that when one shows up, you go, ah, that's an identity. And it's not only true for in this class, but you have to know that for a calculus class, very much so. Okay. They're categorized in 3 groups. You don't have to know the categories, but I think it helps you remember them if you kind of know them grouped. Okay, the first 3 are known as the reciprocal identities. What does it mean to be a reciprocal?
Opposite.
Define what you mean by opposite.
Flip it around.
Flip it around how?
Numerator, denominator.
Okay, so you take a fraction and you turn it upside down to do a reciprocal. Okay, which trig functions are reciprocals of each other? Which ones do you find by flipping them upside down? Sine and cosecant. Okay, sine is y over r, cosecant is r over y. What you said? Cosine and secant are reciprocals, and then, of course, tangent and cotangent. So, yeah, the first three identities, we already know these three. We know they're reciprocals. So, I am going to write in the form cosecant is equal to the reciprocal of sine. It's 1 over sine. You'll almost always be changing cosecant into a sine. So that's the easier version to use. You could say sine is equal to 1 over cosecant. That's very much true, and it's correct, but you just will hardly ever use it in that form. Can't say that I've ever used it to go that way. Usually I'm trying to get rid of a cosecant, and I'm getting rid of it by putting in place a 1 over sine. So the same way, the second one is secant is 1 over cosine, and usually we're getting rid of cotangent and changing it into 1 over tangent. Okay, the one thing I will get picky and mean and nasty about, you must have angles with your trig functions, and it's very tempting in this section because we'll have a variable there most of the time, not all the time. It's very tempting. People want to just not write a variable at all. I don't care whether you write thetas or x's, whatever variable strikes your fancy, but there has to be a variable. You have to have an angle with your trig function. Trig function doesn't mean anything without an angle. It's absolutely essential. Okay, those are the first three. I number them because it makes it easier for me when I'm teaching to say, hey, look at number 4 or look at number 7. You do not have to know them by number. I just number them to make it easier. All right, then there are what we call the two ratio identities. They're numbers 4 and 5. Okay, the ratio identities, what's a ratio?
David, you got this one.
What? He's not jumping on what's a ratio? Say that again. Something to something. A number to a number. Something, so you got something over something. Well, I need to take you back a moment here to our good friends, the Stick Your Rotten Crazy Xylophone, which we, of course, all still know and love. What's wrong with Stick Your Rotten Crazy Xylophone? And I'm sticking them over here on the board because you need to be able to look at them fairly frequently. So, we know that, according to our Stick Your Rotten Crazy Xylophone saying, we know that tangent is y over x. Do we all agree with that fact? Okay. Mathematicians love to take formulas and equations and play around with them, the algorithm, and see what they can create with new. So somebody got the brilliant idea and went, oh, look, suppose I decided to take both of these times 1 over r just for fun. What would I have now? Y over r over x over r. And that's perfectly legal to multiply the numerator and denominator of a fraction by something. So what they did is fine. So what's y over r? Sine. And what's x over r? Cosine. What you just found out is that tangent of any angle is the same as the sine of that angle divided by the cosine of that angle.
That is so dumb.
That's not dumb. That is awesome.
That is dumb. Why would you do that?
So now you have a connection between tangent, sine, and cosine. You know a relationship between the two of them.
Like, wait. To be realistic, this is so dumb.
Okay, so I'm going to kill that.
You just killed a mathematician. Did this.
No, you are going to love this.
She did.
I'm sure he's long dead.
Because if he isn't, I'm going to go find him, seek him out, and,
all right, cotangent then. This is common sense. If tangent is sine over cosine, what's cotangent? Cosecant over secant, Evan, no one can hear. What did you guys say over there? I got a cosine over sine. How do you know tangent's related to cotangent? They're reciprocals of each other. So yeah, all you have to do to get cotangent is flip this tangent upside down. It's cosine over sine. Now the hard part of that one is keeping straight which is which. I always remember cotangent as cosine on top of it.
How do you ever change it?
Actually, you're going to use it so much, tangent, sine over cosine, that you're not going to forget it because you are going to use it all the time. These 8 identities, particularly the first 6, you use so frequently that you will have no trouble learning them.
But there's 5 there. So.
Yep. I got 6, 7, and 8 to go. They are known as the Pythagorean identities. Wonder why they're called the Pythagorean identities. Could they be related to the Pythagorean theorem by chance? You think? Well, I got to take you back here once again. You remember our fun little triangles we've worked with, and our x's, our y's, and our r's? What does the Pythagorean theorem say about that triangle?
X squared plus y squared
Equals r squared. Okay? Nice basic Pythagorean theorem. Well, like I said, mathematicians love to play with formulas. So somebody got the brilliant idea, hey, I want to make it equal 1 over there on the right-hand side. How do I get rid of r squared and make it become a 1? You want to get something to become 1? You divide it by the same thing it already has. If I divide by r squared, won't that get me a 1? But of course, if I divide one thing by r squared, I have to divide every single term by r squared. So, yep, the right-hand side is now 1, but I have x over r, both of them squared. Ever seen x over r anywhere before? X over r is cosine. So this is, since they're both squared, this is the same thing as saying I have cosine squared. And then I have a y over r. Y over r is sine, and since they're both squared, I have sine squared. So this is one of those identities that doesn't seem like it's possible.
Why would you throw r's in there? Dear God.
Because it was fun to play around with the equation and see what happens. So what this is saying is if you take any angle, people have a hard time believing this one. If you take, say, 30 degrees and do the cosine of 30 degrees and square it, plus the sine of 30 degrees and square it, you'll get 1. You could take the cosine of 2,952 degrees and put it in for both angles, and it will come out equal to 1. Doesn't matter what it is. It always comes out equal to 1. That is probably the most useful identity of them all. It connects sine to cosine. You've got some way mathematically to connect sine and cosine together. You'll notice most of these others, they may use a sine and a cosine in them, but you don't usually have sine and cosine in the same equation. And here we add in with tangent, but then you got tangent mixed in too. Yeah. You did learn them last year. It is the very last thing I taught you last year. Right, it's the freshest in your mind. Okay, usually this one is actually written with the sign first. It doesn't really matter, but in my brain I always think of it as sine of whatever angle squared plus the cosine of that same angle squared has to equal 1. That's a biggie. Okay, anybody want to guess how we get 7 and 8? Instead of deciding to divide by r squared, somebody got the brilliant idea, let's divide by x squared and y squared. That's how we get the other two. So if I say, okay, fine, this time I want to divide them all by x squared. What do you get when you have x squared over x squared? 1. 1 plus y over x is tangent squared. R over x is secant squared. And ta-da! You have found identity number 7. Oh, thanks to you. I forgot to check. We'll be back.